Yes.
All right, cool. Hello everyone. I am a fourth year PhD student at Purdue Aeronautic and Astronautic Engineering Department, and today I'm very happy and honored to be here to give the presentation on our research on the safe and efficient traffic management in the future UAM system. And the topic in my presentation is just the safe and efficient traffic management in the future UAM, and I'll provide some overview of the UAM and the traffic management of the UAM. Then we will present some of our like new perspectives on how to design the unmanned aero system traffic management and offer our mathematical tools, models, and theories to support our design on this traffic management system. And we will also discuss like the attack approximation and rejection for the unmanned aero traffic system under our framework. This is part of like a current ongoing research. So to start with some background, like we are all witnessing like the rapid development of the UAS technology, and both in like the research and commercial implementations, and more UAS are both for like a personal use or commercial use are registered in the FAA every year, and over 1 million UAS has been registered by now, and 360,000 of them are going to be put into commercial use. And the UAS and the urban air mobility in general seem to have like a great potential in reducing the economic cost due to the longer commute times of the ever increasing ground traffic. And particularly, the UAM have the application that covers the local mobility, such as air taxis or freight transportation, like the last mile delivery, and the civilians and infrastructure inspections. And the corporations like Uber, Avalator, and Kitty Hawk, Volocopter, and EHang are investing in prototype developing and regulations making with authorities. So as a result, like we will be seeing like great numbers of UAS in the civil aviation domains. However, the recent transportation research has been focused on the UAS assisted traffic. Like none of us has seen the UAS as a body of the traffic. Like UAS themselves can cause like a great amount of traffic, even congestion with some increasing volume, and UAS should be studied as the body of the traffic. And this is the focus of my research. So the UAM by definition is just a manned and unmanned like air traffic system, like operating below the altitude of traditional air national space. And in our research, we limit ourselves to unmanned aero system, like under our topic of the safe and secured, like unmanned transportation management. And the unmanned air traffic system management and the UTM is just a community-based traffic management system where the operators and the entities provide the operation that support services that are responsible for the coordination, execution, and management of the operations, and the rules are established by the FAA. So to summarize, just the UAM is just the traffic and UTM is the traffic management system. But what is the UAS traffic? Like none of us has actually observed the true UAS traffic, and since has not come yet, and it is something in the air. I mean, it's literally in the air. But yeah, the policymakers and the research institutions and the commercial corporations are communicating and try to understand and how to come to agreement on what is the UAS traffic and how to manage it. So this is where also my research goes to. So what is the UAS traffic? So is there like the single UAS hanging in the air on the left picture, the UAS traffic? Certainly not, right? And is there like the US group doing like a formation maneuvering on the right picture, the US traffic? I mean, not quite, right? I think we can borrow some ideas from the ground traffic. Like at the US traffic, I think it's just multiple UAS travel in a shared airspace under different operators. So in this process, communications are to be made among the UAS, and the rules are to be obeyed to ensure the satisfactory traffic conditions. And then each UAS should be able to finish their own tasks. So stem from this basic understanding of what UAS traffic, we can explore the unique characteristics of the UAS and US traffic and propose the right structure or the right framework of the UAM or the UTM, then we can propose the right problem that is associated with those characteristics and explore tools and methods on how to solve the problems. So, but first, like I said, it's just still unclear to many of us, how does the unmanned air traffic works? Is it going to be like the traditional air traffic where everything is just under monitoring and authority, or is going to be like the ground traffic where the participants of the traffic kind of like have a lot of autonomy? Like how does the traffic management can effectively manage the macro level traffic behavior as well as the agent level, the individual movement of the participants? I think it really boils down to very detailed policies and rules, like how US should travel in the public airspace and how the infrastructure and available onboard measurements and communications be like. And in order to answer this question, let's take a look at the existing form of the traffic. Mainly, we have the crewed air traffic and the ground traffic. Each has its own pros and cons. For air traffic, the cost for any accident is enormous. Therefore, the safety is the priority of the air traffic. And to achieve the safety, the current practice is for each airline to file a flight plan to the air traffic controller and execute the flight plan after the flight plan is revised. And during the flight, the air traffic controller kind of responsible of monitoring each flight and sometimes give runtime commands to each aircraft. And in this way, the traffic is managed in kind of the centralized fashion that is to guarantee absolute safety and security. And the congestion control is also implemented directly by change the rate of takeoff and landing, that is the capacity of the airport. And this has been the practice for decades. And the disadvantage of such practice is kind of obvious. Like the biggest issue is the scalability. The flight plan generation, revision, and refiling takes a lot of computation time and communications efforts. And this is also an issue for the current research in the air traffic management. They try to resolve this scalability problem. And a lot of existing work discussing the operations of the US traffic take this crewed aircraft traffic management system as the template. However, this is not what I really had in mind. On the other hand, we have like the ground traffic. In ground traffic, the navigation and the maneuver is kind of like done in a decentralized fashion, right? It can handle like a very high volume and high frequency operation. However, the macro level flow rates or capacity is hard to characterize or controlled by the individual movement of the vehicle. And then oftentimes traffic regulation is not always obeyed for the sake of safety. We can oftentimes see some reckless drivers on the road that can harm the public safety and the traffic efficiency. So all these pros and cons of air traffic and ground traffic make me wonder, is there any form of traffic that can take the best of the both sides? Can we have like a decentralized event-like behavior for each UAS, such as the control or path planning is done by each agent to improve scalability, but the traffic management system will still have some authority over the behavior of the UAS, such that the safety can be achieved? And how can we bridge the individual movement of the UAS with the macro level flow control of the traffic system? So these are the two questions that I'm trying to answer today. And also, there are some technical challenges that should be addressed for the air traffic management system, such as mission planning and the separation from hazard and the contingent management and demand capacity balance and the traffic flow management and spacing. So with these ideas and challenges in mind, we have some new perspective on how to design the UAS traffic management system. So we first noticed that the UAS actually relies on the system autonomous control or decision supporting tools rather than the human pilots. And the fact that the behavior of UAS is more governed by the autopilot instead of human operator reveals that the UTM may regulate the collective UAS traffic behavior by adopting certain control protocols. So in other words, if all the UAS can agree on a predefined control protocol in certain airspace, then the collective safety and efficiency assurance for the UAS traffic can be converted into a control protocol design problem. And by directly regulating the UAS traffic behavior at the control level, the UTM and the operator UAS can reduce the effort of trajectory planning and reviewing significantly. So with those perspectives I have just mentioned, I present my work on the control-based UAS traffic management strategy. And in this work, we redefine the roles and the responsibilities of the main characters in the UAS traffic systems. And we formulate the main objective and constraints for the traffic regulations. And based on the objective and constraints, we developed a decentralized control protocol for agent-level traffic regularization. And most importantly, we characterize the system-level flow from the agent-level control. And lastly, we can propose the hardware requirement for the UAS in the control protocol-based traffic management. So as we introduced earlier, in order to achieve a safe and efficient traffic management system, we need to redefine the roles and responsibility of the UAS based on the unique characteristics of the UAS. So in our framework for the UTM, we have 4 main characters or roles in the operational level: the UAS operators, the infrastructures, and the UAS, and finally the unmanned aircraft management system, the UTM. And we will first introduce these roles like in the order of design process. And first, we have the UTM, who actually defines the UAS traffic networks, such as the nodes, links, and the virtual boundaries for the UAS traveling it. And also, each traffic link and regulations, each traffic link has its own regulations and rules for the UAS traveling in it, such as the speed limits, the minimum separation between UAS, and the minimum desired distance to the virtual boundaries, and also the feasible landing areas. And based on the rules and the regulations associated with each link, a set of control protocols can be designed. And during the operation, the control protocols are broadcast for each link, and the UAS that follow the control protocols after enter the link. And the different sets of control protocol need to be designed for each link to take account for different factors, such as weather, human activities, emergencies. And during the operations, the best suitable control protocols are selected for the link and broadcast. And second, we have the infrastructure. And the infrastructure is responsible for broadcasting the control protocol. And the broadcasting is also beneficial for the contingent management. And in the event of unexpected, a suitable set of control protocol can be broadcast across the affected airspace, and the UAS in the airspace can have a safe and immediate response to the unexpected event. And the infrastructure can also be responsible for monitoring the traffic system for any possible anomaly and intruders. And then we have the UAS operators that design the low-level controllers, such as from the thrust or voltage to the accelerations. And in order to follow the high, those kind of low-level controller are designed in order to follow the high-level control protocol that are broadcast by the UTM. And they also the operators are also responsible for designing the sensors and filters and the broadcast receiver in order to implement the control protocols. And before each task, the UAS operator determine the origin and the destination of each task, and then determine the switching of the control protocol at each junction for the UAS. And finally, we have the UAS. And during the operation, the UAS can take the measurements and estimate the state of itself and the relative information with respect to other UAS and obstacles, and execute the broadcast control protocol in each link. So this framework actually calls for a great range of possible research in order to implement this whole framework. And in our work, we focus on the control protocol design part. We first define the problem of traffic regularization. We assume that the UAS with the autopilot system is modeled by the double integrator. the states are just a three-dimensional coordination of the UAS, and we call the connotation of the state vectors of all UAS a configuration, that is the QI. And we introduced the notion for the traffic regulation for a single link. A single link is defined as a tuple that has the physical space and the desired velocity, which is a vector, and the minimum speed and the maximum speed, which are scalars, and the minimum the desired pairwise separations and the minimum pairwise separations, and the desired separation from the boundaries and the minimum separations from the boundaries. And the physical space of the link can be defined as the polytope represented by the linear inequalities. And we also define the index set for the UAS that's in the link at the time t, and the index set for the UAS enter the link at t1. So if there is no UAS entering the traffic link after the t null, we have the following objective in the asymptotic sense. So the objective 1 requires that the velocity of all the UAS in the link converge to a desired velocity, and objective 2 requires that the separations, the pairwise separations of the UAS are greater or equal than the desired separation given sufficiently long time. And our O3, which is the objective 3, actually requires that the position of all the UAS in the link converge to the desired separation from the virtual boundaries. And also we have 3 constraints. The constraint 1 requires that the boundedness of the velocity or the boundedness of the speed actually, and the constraint 2 requires that the pairwise separation of the UAS should be greater or equal to the allowed ones for all time. And constraint 3 requires that the boundary clearance should be greater than the defined minimum at all time. So if there is UAS entering the link after certain time instance, then we only make sure that all the constraints are satisfied. Therefore, the incoming traffic won't cause any rule violations. So when there is a fixed group of UAS in the traffic link, the UAS like behavior regulation problem can be easily solved by the classical artificial potential field based algorithm. We can define the potential energy function for the pairwise separation, boundary clearance, velocity tracking, and lastly, we define the Hamiltonian function as the sum of those potential energies. And the decentralized control protocol is just a negation of the gradient of the Hamiltonian function. So we have like our first result. This result is pretty standard. It states that if under our control protocols, the configuration of the UAS will converge to the desired equilibrium that are stated in our objectives. This is just the first part and the second part of the proof, the theorem. And then the next half or the rest part of the theorem just stated that if the initial configuration is in some sublevel set of the Hamiltonian function, then the constraints are to be satisfied all time. So before I proceed, I want to spend a few words on the proof of this result, since it leads to our later work. So in the proof, we show that the convergence is to desired configuration of the UAS traffic is given by the convergence of these Hamiltonian functions. And we use the LaSalle invariant principle to show that the equilibrium is actually desired one. And as for the constraint satisfaction, if the initial value of the Hamiltonian is less than the minimum possible value for the energy function or the Hamiltonian function for any constraint violation, then by the monotonicity of the Hamiltonian function, we argue that there will not be any violation of the constraint from the time following. So it can be seen from the proof that the convergence of the Hamiltonian function and the initial values of the Hamiltonian function play the critical roles in the configuration convergence and constraint satisfactions. So based on this first theorem, what we have achieved is a kind of just distributed control protocol that guarantees that the group behavior regularization in a traffic link. What we have not addressed is that what about the incoming traffic of the link? Like how to characterize the flow rate of the incoming traffic? So to solve this question, like we said, the convergence and the initial value of the Hamiltonian function is very critical. If we can know the convergence rate of the controlled system, then we can estimate it. We can estimate the Hamiltonian value of the traffic. Then we can estimate it, how much traffic is allowed into the traffic link without any constraint violations. So mathematically, we want to know the convergence property of the following augmented Hamiltonian system, this one. And the form of this Hamiltonian system actually reminds me of something else. So it looks like some continuous time version of the momentum method for solving unconstrained optimization problem with the objective of psi. Like examples for those algorithms are like the heavy ball method or the Nesterov accelerator gradient method. And I believe the convergence property of this system is somewhat like close to the convergence result for those algorithms, except for those are the discrete time algorithm, and this is the continuous time version. And during this work, I actually hoping to see some like direct results I can use, but there wasn't any at that time. So I guess my following result is not so trivial. So we have some like first we have some smoothness condition on the function with the Lipschitz constant L, and and the second assumption is the lower bound on the Lipschitz constant. And note that the second assumption is not so restrictive, since if you have some L prime that is greater than L, then the assumption 2 is still satisfied, and then there are always some like constant L such that assumption 1 and 2 are both satisfied. So with this assumption, we introduce one of the most important lemma of this part of my work. And the following lemma says that if the initial value of the gradient and the Hamiltonian function and the velocity are finite, then the infimum of the gradient norm square and the velocity norm square is converging at a sublinear rate. And note that the left-hand side is just a scaled magnitude of Q double dot. And by this lemma, we can see that the infimum of the gradient, the infimum of the acceleration is converging at a sublinear rate. And actually, this is not so surprising since the sublinear rate is well established for the first order method for solving non-convex optimization problems. And this is my attempt to show that this rate for the continuous time momentum method. However, we noticed that the previous lemma was not directly used in our problem because it only provides the lower upper bound on the accelerations or the gradient force, but not actually for the Hamiltonian function. So this following theorem 2, actually provides some insights for the convergence rate of the Hamiltonian function under some proper assumptions. So first, let's assume that the gradient actually satisfies this inequality, and this is actually can be understood as some local convexity around the equilibrium point. And then we can show that the Hamiltonian function is actually convergence at a sublinear rate at constant lambda, and the lambda is defined as following. So now we have the convergence rate of the Hamiltonian function. So with this convergence rate of the Hamiltonian function and our control protocol, we can find a suitable method for design the inflow. And we can have like a discrete instance for the UAS traffic system for the UAS to enter the traffic link. And this proposition reveals the relation by the amount of Hamiltonian increase and the time window between each entry time. So this proposition says if we know the amount of Hamiltonian function increase at each time instance is below some predefined threshold, and then if the time window is long enough, then the Hamiltonian function is always below that threshold. And the length of the time window is determined by the convergence rate that is established by the previous theory. So basically, another way to look at this proposition is that we know that how fast the Hamiltonian function will decrease, and if we have a long enough time period such that we can know that how much more energy and we can inject to a traffic link. And then if we have some estimation about the potential energy that each entering UAS can bring, we can quantify the maximum allowed number of UAS can enter the link at each time. So it's just simply the maximum integer solution for this quadratic inequality.
Jiazhen, I'm sorry for interrupting you, but how do you go? I do apologize for interrupting you.
No, it's okay. Yeah.
How do you correlate? Energy with capacity?
Yes. Right here, the capacity is not directly correlated by the energy. It's correlated by the estimation of the energy that each entering UAS can bring, and then we solve this the quadratic inequality, and we get a solution, which is the number of the UAS can enter the traffic link for each capital T period, and this quantity, this ratio of this number m and the capital T is the capacity of the link. The capacity of the link is just how many UAS can enter a link at each time, right? This is the definition of the capacity, and the ratio of the capital M here and the capital T here is just the ratio of how much UAS can enter at every capital T. Yeah.
And,
So
your energy is associated with what? With kinetic energy?
no, those energy actually is associated with the initial separations between those entering UAS and how much velocity difference between their velocity and the desired velocity. Though those are quantified, those energy, the kappa and the gamma. Yeah.
Thank you, Jiazhen.
Okay.
Thank you.
Yeah. Yeah. But let me know if you have any other question. Yeah. The question is very much appreciated. Yeah. So I will just continue. So yeah, I mean, this is kind of this actually explain this the question kind of explain this lemma quite well. So the proof of this lemma and the previous one is just a very basic algebra. So at this point, we have finished showing how to connect the agent level control design to the macro level flow design. And by adjusting the parameters such as the minimum pairwise separations or the some parameters in the potential function, we can actually be able to change the inflow rate or the capacity of each traffic link under different scenarios. Say sometimes there is raining, we can just increase the pairwise separations, and by the inequality here, we can indirectly actually change the inflow rate of a traffic link. So to validate our result, we
May
should
I ask a question before you go further? Where are you bring? What about the communication? Where are you bringing the effect of communication on?
Yes, actually, after I show the slide of my simulation, I will discuss how the communications are achieved. Okay, yeah, yeah, that's a good question. Yeah, yeah, very important actually for the implementation of this algorithm. So, so let me finish my simulation results part. And so we show that the UAS entering a link that is using our control law and entry conditions. So we show that the configuration of the UAS every 20 seconds, and this simulation shows that our design control protocol and the entry condition, the UAS are able to enter a single link safely and regulate their speed and the separations. And the fundamental benefits of our control protocol is not actually just to achieve this convergence to the desired behavior, but actually to increase the amount of traffic link can take in this short period of time. So under our simulation, at least 2 UAS can enter the link at every 20 seconds. So this allows 360 UAS to travel across this link per hour. And this great amount of traffic is kind of formidable in the classical trajectory file and the review process for the traffic management system, like the crude air traffic management system. If all the operators just to file their trajectory and to be reviewed individually. And this trajectory reviewing for this amount of traffic can also be very overburdened for the traffic controller. Also in this slide, we have shown that the adoption of our control protocol in the split link. We see that actually our algorithm can also work in some more complicated scenario when one link split into two links. And to answer the question that the professor just asked, we say that based on our proposed framework and control protocol, a receiver is required on the UAS to receive the broadcast control protocol in each link. And a certain encoding and decoding protocol need to be designed in this process to prevent any potential cyber attack. And the control protocol first assumes that the position and the velocity is estimated for each UAS. And this can be achieved by the integration of inertial measurements of sensor such as gyroscope, accelerometer, also with the global positioning system, which are technically equipped on the UAS. And however, the state estimation for some highly nonlinear UAS dynamics is non-trivial, and the nonlinear common filter can be used to estimate the state. And to answer the question regarding the communication, for the inter-UAS separation, the relative distance measurement is required, right? So although in our work, each UAS should have the relative state information for all other UAS, however, it is sure not practical to assume such acquisition of the information in the real-world traffic, and it's not necessary either. So since the potential function in our control protocol actually has the finite support, therefore only relative states in the support of the potential function is necessary. So in the other word, only the relative states for the information of the UAS that are in the desired separation range is needed. And the one UAS can use sensors like a radar, lidar, or sonar to detect those relative position informations. And also the limited amount of information that is actually necessary can greatly reduce the state measurement and the computation for the control practice. I think that's my answer to the previous question. Okay, so this is the part for the hardware requirements. And also, I will just introduce our current work. So this is the previous ones are just our framework and the methodologies on how the normal UAS operation should be like to improve the scalability of the future UTM system. And as the second part of my work and my current work is just how to make the UAS that is resilient to the cyber attack based on this proposed framework. So we turn our attention to the question, what is the cyber attack isolation in the context of UTM? So it can be seen from our framework that the control structure is very vulnerable, and in the sense that the command signal or the control protocol is received in the broadcast sense, is received in a network, and this leaves opportunities for the attack to intrude the control channel. And it may not be feasible to regain the control authority for the attacked UAS immediately. So it is urgent to identify such aircraft for future evaluation and for immediate isolation. So meanwhile, it is also desired that the healthy UAS can stay clear to the attacked UAS while accomplish their own tasks, such that the whole UAM system can remain efficient. So therefore, the current stage of my research is that we have to do the attack modeling, that understanding the form of attack, and the attack identification, that is identify the attacked UAS, and the attack isolation, that is for the healthy UAS to remain separated from the attacked UAS, and the attack mitigation, that is to regain the efficiency of the presence of the attack. So in our formulation for the attack, we rewrite this for control the dynamics of UAS as the first order system, where the states are just the stacked vector of the position and the velocity, and we let the both x to be the stacked state vector. Hence, we have the function f as the abstraction of the normal dynamics, and we take the inputs of the state of information of all other UAS as the normal dynamics. On the other hand, we can have the attack dynamic, which is unknown, and might also take the state information for other UAS. And this formulation of attack is rather general and accounts for a broad scope of attack scenarios, such as the loss of communications and sensing, of loss of the control authority, and data injections. So in order to identify the attack, we first assume that all the state information are available. So the information is generally achievable for the simple double integrated dynamics. And the position information can be achieved by direct measurement, and the velocity can be either by measure or estimated by some high-gain observer. And with the state information available, the attacked UAS can actually be identified rather easily. And for each UAS, we can have the estimated model for the nominal dynamics, then compared observed state and estimated the state to identify any attack. And in the presence of system uncertainty or environmental noise, we can define the residual as the integral of the state difference and compare to any threshold. And this actually technique has been effectively studied in the literatures. So in the case of the communication or like a failure or hijack attack, the control channel for the UAS are likely to be jammed. So there may not be feasible method to regain the control authority for the attacked UAS immediately. So this is crucial to predict the attacked UAS, such that the operator, the traffic manager can capture and track the attacked UAS, and the healthy UAS can still avoid the attacked UAS while finishing their own task without losing too much efficiency. So our current approach is to develop an online attack model learning module to approximate the attack dynamics of the UAS. The goal is to achieve the parameterized approximation model where the theta is the fitting parameter that is satisfying that the minimum of the L2 norm, that minimize the L2 norm of the attack dynamic and the approximate dynamics. And in the classes, approximators such as polynomials, radial basis, adaptive or fuzzy functions can be used as this function approximator. But if one has a good guess of the types of attack that might happen, the attack model can just be the linear combinations of all the possible attack dynamics. And when the attack happens, then one parameter is supposed to be non-zero or much higher than other parameter. And actually, in the literature or the real world, the implemented attack that has been done in the lab or to have done in the real world scenarios, the attack dynamics are actually quite easy. They are just like a free falling or drifting or haunting, and those are just linear dynamics. But right now we just take this general nonlinear form as for the generalities. So to get the best approximation of the parameter, we use the Lyapunov synthesis approach, and the adaptation rule is following. We have the adaptive dynamic and we have the approximation dynamics, and we updated the parameters by using the error between the approximated dynamics and the true observed states of the attacked UAS. And after the attack dynamic approximated, the question is how can we design a robust controller on the health agent to remain safe separation and also obey other safety constraints. So our approach is this. So to solve this problem, our plan is to use the reachable set estimation for attacked UAS. And if the model is fitted, then we can have the nominal model for the UAS with the noise or the approximation error as the noise of this model. And then we can compute the reachable set as the subset of the state space where the UAS can reach for the given any possible noise. And later, we kind of plan to develop the algorithm to convert the over approximation of the reachable effectively, such that we can create the new virtual boundary for the healthy UAS to avoid the timely that is under our previous framework of the nominal operation of the UTM. And right now we have done some work on the approximation of the attack dynamics, and the attack dynamics is first assumed to be a linear dynamic, such that the dynamic that the UAS will operate in a sinusoidal motion, and then the attack dynamic can be approximated effectively using the previous Lyapunov synthesis function that we have just introduced. And in the later, we are actually trying to develop the efficient algorithm for the over approximation of the reachable set for the attack dynamics. So this is for my presentation, and here are some selected references if you are interested. And thank you. And I will want to give like a special acknowledgement to my advisor, Professor Duncan Sun, and my co-authors, Dao Sun and Professor Huang. And I'm open to any questions and ideas. Yeah.
Great, thank you so much.
All right. Thank you.
Thank you.
Jiazhen, can you go back to your publications?
Yeah,
Because
yeah,
I
yeah.
will definitely read them.
Yeah, this is my the publication that is related to the topic I just mentioned.
One of the things that I don't get is that can you hear me?
Yeah, I can hear you. Yeah.
You cast the cyber attack problem, not as the cyber attack problem, not as an estimation problem, but as a control problem. In other words, if I'm gonna hack your UAS, you're gonna design a controller that they can still go to their destination, or you are trying to figure out if something is wrong. Like do a residual on our observer in that case.
Oh, you mean like a designing or observer for the attack the UAS?
Yeah, design an observer to figure out if something is wrong in the first place, to detect the attack.
I think my answer to that question is that it is like a tricky, like how much information one actually need to identify such an attack. And for some like a general nonlinear attack, you must like have some acquisition of what's the nominal attack, a nominal behavior should be. So in that case, I think we must the traffic monitor or the infrastructure should have like the acquisition, should have the information about the normal attack, and they simultaneously simulate the UAS behavior and they compare to the actual UAS that is measured in the space. But yeah, and by that they compare the two trajectory for the to identify attack. But so for the observer, I mean, your question is like, is there any like a idea about how to design observer? So my answer for that question is that I assume that all the state information is known because that I use the double integrator dynamic, and those kind of information is actually easy to acquire, right? It's just position and velocity. So there is not so much attention from me that is given to the like observer design for the attack approximation, for the attack identification. But I believe the ideology is still you use the observer and compare and define a residual and compare the residual to some like a predefined threshold. Is that correct? If I'm understanding you correctly. So
yeah, this is because in fundamentally I view cyber attack as being an estimation and detection rather than a control problem.
Yes, indeed. Yes, indeed. So from my understanding, I assume that this kind of like a attack identification strategy can be implemented. It actually implemented in some crewed aircraft that they just use the residual to define. So I didn't pay too much attention to like any novelty in the formulation of this kind of attack identification. I assume that it's just gonna be a residual generation problem. But maybe there are some. I think there are much more interesting questions that if the attack can be stealthy, such that when you compare the measurements or the Y in the control scenario, it's very hard to tell the difference, right? It's from my understanding like the novelty then there probably will be some difficulty that identifying those attacked. However, in this scenario, I think that the very meaningful attack will be, okay, you will have like different measurements. Suppose these are just position, and then however the velocity can drift away. But this is really the case for the UAV. I mean, you have to structure a very special case of the linear dynamics to construct those like dynamics with a very like a non-trivial zero dynamics of the linear system. But I don't see how this is a general case for the UAV. I mean, but yeah, but some possible discussion that stealthy attack on the UAV can be discussed. Are those attacks can actually be implemented on the UAV, and then we can discuss like how they can be identified. Yeah, this is my response.
What you have done is excellent work, no doubt. But you might, for your curiosity, from what I understand at least, because you have a very complex math over there, from what I understand, the stealthy attack in your model create different Fs, create different functions. It would be interesting if you actually view the attack as being an exogenous signal. Like it's going to be a signal that it's injected from some place in the sensors or in the actuators, and then it creates some different story. So it's some sort of a measurement mismatch instead of a model mismatch.
Yeah, and I totally agree that the attack identification for like the nonlinear UAV dynamic and also the dynamic I just proposed can be extensively studied by assuming like a very practical and complicated input channels. And but for my work, I think the part I just presented, I kind of just focus on how the traffic system can like accommodate for if one particular UAS just showed up. Yeah, so I guess my work and your question kind of just focus on different part of this whole logic, like a whole operation logic, the whole different stage at this operation. Your like attention is on the attack identification stage, and my attention is at the attack rejection as a traffic system. But I think all those work actually cause a very broad class of research. I do believe there are a lot of things need to be done in this process. And my understanding for this may be a bit shallow, actually. I do agree with that. But I'm more than happy to have more discussion on more detailed attack possible forms and how to identify them. Yeah. All right. Thank you very much.
Okay, any other question? Okay. Well,
I have if there is no any other question, I do not want, I mean, obviously you're having very in-depth mathematics there, and it's very difficult for me, for one, just for a presentation to follow most of the things. But if I understand correctly, you are solving an optimization problem using dynamics. And at some point, I've noticed that you have used Lassalle's theorem, which has to do with invariant manifolds. So my question is the following. Based on your modeling assumption, is there a case that there is an attractive manifold that may cause to the system oscillations? In other words, this thing starts, doing like a spring or something.
Right. Actually, good question. Good. You can finish your question. I think I might be interrupting you.
This was my question.
Yeah. Actually, just imagine this case. Actually, this is a very good question. Me and my friend actually had an intense discussion on this scenario. Is like how to deal with this. Like, suppose you have like a traffic link that is on. This is your boundary of the traffic link, right? And then in between the traffic link, there are like a couple more like a UAS like aligned perfectly, right? And then in this kind of in this scenario, the pairwise separation may still be like a smaller than the desired one. This is unwanted, and then there is no way for them to actually escape from these cases. And then since in each agent the control input is zero. Just think about like on the left there is US pushing it, and on the right there is US pushing the other way, right? From the potential energy approach. And then in this case, is exactly what you have just mentioned. This is a wanted equilibrium, and maybe on this level, on the aligned level, they will have some sort of oscillation. But what I want to say is that maybe this is not like for cases that we need to worry too much about, because any perturbation it will drive the system away from this unwanted equilibrium. This is an unstable equilibrium, and actually this is a general assumption that is almost all the equilibrium in the for the dynamic system is is the desired one. That means this kind of configuration is very tricky and very hard to actually be there at the first place. Yeah. So did that answer your question?
Thank you, Jiazhen.
Okay, thank you.
Let me ask you a follow-up question. Do you know the kind of attack beforehand?
Yeah, actually, I have read some articles. Currently, there are some attacks, like the GPS spoofing attack, and then there are some attack channel robbing. This is like the most severe kind of attack. I actually see a website that there are actually some people develop the software that can just rob the control channel. I have read a website. Yeah.
So you're assuming a white box then?
Yeah. Maybe we don't know what's the exact attack gonna be. Yeah.
Yeah, but no, by white box meaning that you know the type of attack.
So my formulation is actually account for both cases. If we don't know that what's the actual attack gonna be, we can use function approximators to approximate the attack dynamics. But however,
this is offline.
No, this approach is online. This approach if we use if you use the polynomials or more complex, like I say, neural network, we can be arbitrarily close to the attack dynamics. I mean, in a compact set for sure. But this is kind of the restriction on this one.
Okay.
Yeah.
How do you set your upper bound threshold?
I'm sorry, what?
How do you set your, if you go, how do you set your, right here in this one. How do you set your upper bound threshold?
And I think this one actually can be done by integration on the possible the maximum magnitude about the noise or the model uncertainty. You integrated for over the T to capital T, and then you kind of know what's the maximum effect can the system noise create. Then anything beyond that can be understood as attack. Yeah. I mean, this is actually the common practice for in the literatures. And
so then how can you distinguish between attack and also failure in some sensor?
I think in my formulation, it does not differentiate that. Since behavior wise, they are both abnormal. They're both abnormal behavior. So we actually differentiate those two cases by if the behavior is normal. When the behavior is abnormal, then there can be cases where the sensor is failing or there can be attack. But my focus on this formulation is on the healthy part, on the healthy agents, how to avoid that abnormal UAS. Yeah. So this is my understanding for this attack rejection in the scenario of traffic system. But yeah, there can be a lot of work to be done, like for how to identify individual UAS and regain the control, or to differentiate if it's a sensor failure or actual attack that you can no longer regain the control authority. Yeah, I mean, but I didn't pay my focus of work isn't on that. Yeah.
Are you looking for a number of frame to say that it is whether this is an attack?
I'm sorry, I didn't like it.
For a sequence of point to say that whether this is it is an attack or this is maybe something to do with sensors, environment that I missed. Information was not conveyed properly.
I think my understanding to your question, or my response to your question, is still something to do with their threshold, since they are actually kind of like a maximum possible or maximum estimation about how much uncertainty that it can cause from the sensors or environment, and then anything beyond that we treat those as attack. But this might not be a most like a sophisticated way. Maybe there are some attacks that can keep the residual like below the threshold, but I think that's also a really good like a research direction.
Thank you.
Mm-hmm.
Okay, is there any question on the cyberspace?
No, I have a question. My name is Nagasa. I'm working with Dr. Karamidini. On your first work, you say that you will keep the separation between the two UAVs. So if the separation is failed, what is the control action you will take? What is the proposed control action you can take?
I'm sorry, are you asking the minimum separation?
Yeah.
Okay. What was the question again? I'm sorry. My volume is a bit of. Let me increase my volume. Can you speak a little bit louder? I think I had a hard time capture all the words. I'm sorry.
Okay, you didn't hear me?
Yeah. Okay. Yeah.
So if the separation is a minimal separation is failed due to the sensor or something else, what is the control action UAVs can take as the solution?
Well, what is?
What is the control action can the UAVs can take as the action?
Like what if the UAS separation is actually
failed? Yeah, if it is failed.
Okay, I think in that case, the constraints are violated, then I mean the control protocol is still able to push away the two UAS. However, it's just saying that the constraint is violated. That's it. That's all it is. But the control law is still able to push away. I mean, so my theory on works when works for the constraint to be satisfied all the time. But practically, if you have a initial condition where the constraint are violated, then probably the control law is still working, but the constraint is just the problem is just against my problem formulation. That's all there is. Yeah.
Okay, thank you.
Okay, we have time for one more question. One more question. If not, we're going to thank the speaker. Thank you very much. Okay, go ahead.
Okay, I have a question that you have done some really nice work obtaining information in order to conceptualize how the urban aerial mobility network is gonna look like. So I have two questions for you, two brief questions for you. How big is this network supposed to be? Is it supposed to be Illinois or is it supposed to be Chicago? Is it supposed to be state? Why it's big or it's gonna be an urban city? And the second question I have, just if you can comment on that, Does your concept involves intersecting aerial corridors?
I'm sorry, what was the second question? I didn't get that.
If your concept involves intersecting aerial corridors, like corridors that go through the same point.
Right. Okay, to answer the first question, the capacity of my idea of the network or the capacity of the traffic network under my framework, how big can it be? I think it really depends on how far the US can travel. Like if you are considering like quadruples, and I think their range of motion is kind of limited to maybe not really a city. Some maybe for a city like Chicago, they can only cover part of the city. So I guess the traffic network in that case can be rather small. But if you have like some gas fueled UAV, you can have like the network that cover a wide range, so even a county. But it just really depends on the sparsity of the network rather than the complexity of the network, and it only depends on how far the US can travel, and the different UAS can have like a different layer of network. Suppose you have like a gas fueled UAS, it traveled really fast. Then we have to construct another layer that is above the, like I say, the electricity like fueled UAS, which is travel slower. You have to separate those kind of UAS things. Why? Because in my control law, the convergence rate is governed by this K. The K is probably associated with the dynamic capacity of the UAS, and different type of the UAS should be separated so that this K can be like not very different from each other. Am I answering your question? Yeah.
Just one more thing, the UAS that you are referring to for urban air mobility most likely is going to be eVTOL, right?
I'm sorry, what?
Vertical takeoff, landing, eVTOL.
Oh, eVTOL, okay. Oh, vertical, okay.
Is that right?
Yeah. I mean, it can be right. So the eVTOL can be perfectly modeled on high level as like a double integrator, and this is all true. However, for fixed wings, I want to add a comment for that. For fixed wings, you can use like the Dubinka model. And on the horizontal plane, and you can use like say the feedback linearization to linearize the model, and then you can get a linear model as I just had. Like actually, I mentioned this in my paper, but yeah, you can definitely use the feedback linearization to get a double integrated model for other type of UAVs, say the fixed wings. Yeah.
Okay. Thank you.
And for the second question, sorry, I kind of I'm sorry, I forgot the second question. What was the second question? I'm sorry.
If you can have intersecting corridors, but I think I mentioned.
Yeah, for my cases, actually, in this work, the corridor actually is work at the highway, right? It's just a straight line, and there is no right turn. So from my, I actually had a plan for this, like the continuation of this work. You can have like a roundabout, if you have like two lanes that are intersecting with each other. Therefore, the roundabout can be formulated as a link. But it's like it's curved. The velocity, the reference velocity cannot be like a constant term, but it's just a curve. Like it can be. So in that case, the intersection can be modeled by a straight link connected to a roundabout and connected to other straight link. Yeah. So and the conversion between the link is actually may need like a further discussion, like how to guarantee the constraint violation does not occur during this this transition. Yeah, it's an interesting question, and I actually had a plan for that part. Yeah.
Thank you, Jiazhen. It was a very nice talk. Appreciate it.
All right, thank you. I appreciate your question. Very profound.
Okay.
Thanks.
Thank you, everyone. Thank you.
Thank you.
Have a good weekend. Bye.
All right, you too. Bye.
Bye.